what we covered, guys, the first part of organic, as I said, was a family of hydrocarbons called the alkanes. For those of you that were here for that first part of organic, what is it that distinguishes, that makes a hydrocarbon an alkane? What's the distinguishing feature? Okay, exactly. All single bonds in the carbon chain. Another way to say that is that it is a saturated hydrocarbon. Okay? What we're going to start looking at today is, what if it's not all single bonds? What if there are some double or triple bonds in there? All right? If you see a double bond somewhere in the carbon chain, it's not an alkane, we call it an alkene. Okay? But that's not going to change a lot in our naming scheme. You know, you still count the number of carbons in your longest chain. 3 carbons, meth, eth, prop. So it still gets that prop prefix, but it's not all single bonds, so it's not propane, it's propene. Okay? If something has a triple bond somewhere in the carbon chain, we call it an alkyne. Okay? Same rules apply though. 5 carbon chain, meth, eth, prop, but, pent. It's not pentane, it's not pentene, it's pentyne. Now, what do you think that number 2 in the name, what do you think that is telling us? Yeah, the location of the triple bond. Based upon the fact that this number here is the number 2, have they numbered their carbons from left to right or right to left? Right to left. Okay, now why is that the correct direction? How do you decide how to number your carbons? Yeah, you want to number in whatever direction is going to give you the lowest possible number. Okay? Now, come up here. How come this one isn't called 1-propene? Why is that unnecessary? Okay, yeah. If you put the double bond here instead, wouldn't it still be 1-propene? We would just number from the other direction. If moving the double or triple bond around doesn't change the name, then you don't need a number. So the rule actually is, if your carbon chain has more than 3 carbons, so 4 or more, then you need a number to indicate where the double or triple bond is located. If it's 3 or less, then you don't need a number. Okay, so those are just some other examples. Bless you. All right. So we'll do some practice with this, but it's really not all that different than what we were doing last class. Okay, now there's one other thing before we do any practice with this. What's on this slide, this what's called cis versus trans isomerism, make a note to yourself. This is a concept that applies to alkenes only. Okay? Cis versus trans is an issue that only comes up when your carbon chain has a double bond in it. Okay? So let's just look at this. All right, if the hydrogens are bothering you, ignore them. Let's just focus on the carbons. How many carbons are in the longest chain? 1, 2, 3, 4. So meth, eth, prop, but. It's got a double bond, so it's butene. And what is this 2 indicating again? Yeah, the location of the double bond. Okay. Now look at the difference between these 2 pictures. This one shows the ends of the carbon chain both on the top, whereas this one has the ends of the carbon chain, one on the top, one on the bottom. And that is something different. That changes the molecule. If the ends of the carbon chain are both on the top or both on the bottom, we call that a cis isomer. If it's like this, or it could be this direction as well, that's called a trans isomer. And they're only showing you the boiling points here just to show you that these molecules behave slightly differently. Okay. So it's cis versus trans. Those of you that go on to take organic, they start to use terms when you're talking cis versus trans. They'll call a cis isomer, they will say that it has a boat geometry. Okay, that this is sort of weird, and it may not look like a boat to you. Okay, but having that shape like that, and you know, like there's the water line, la la la, like that's the boat shape, whereas this one over here, they call chair geometry, like a recliner. Okay, so those of you that go on to take organic, you'll hear a lot about boats and chairs and anyway. Okay. Now, do you always have to include cis and trans in all alkene names? No, you don't. How do you know when to put that in the name or not? Well, guys, if you are given a drawing and you're supposed to name it, you only have to worry about cis and trans if your drawing has this X shape, okay? If you don't see this kind of thing and it's an alkene, that means you don't need to worry about cis and trans, okay? For example, look at number 1 here. I'm going to ask you to name this guy in a second. It's an alkene, right? It's got a double bond. Do you see this drawn out in that X shape? Number 1? No. You don't need to include cis and trans in this one. How about in number 2, though? Number 2 you are. And let's do number 2 together. Okay? So immediately the first thing that jumps out at me is that X shape. So I know at some point I'm going to have to put cis and trans in the name. But we'll worry about that later. Those of you that were here last class, what is the very first thing you do when you're given a drawing and you are supposed to name it? What do you do first? Find the longest carbon chain. If the hydrogens are bothering you, ignore them. How many carbons are in the longest chain? 2. 7. Make up your minds. I hear 2, 6, 7, 7. Look. 1, 2, 3, 4, 5, 6, 7. Okay? So maybe it'll be helpful if I circle the main chain here. Okay? What's the prefix for 7? Hept. Okay. Is this going to be heptene, heptine, heptane, what? Heptene. Okay. Will I need to indicate where the double bond is? Yes. Remember, the rule is if your longest chain is 4 or more, then you do need to put a number. So let's decide, how do we want to number this main chain? Should I number from left to right, or would it be better to number from right to left?
Left to right.
Why left to right? Yeah, that's going to put the double bond on a lower carbon, a lower number. So let's call this 1, 2, this is 3, 4, 5, 6, 7. Okay. So where is that double bond? Which carbon? 3? Okay. Okay. What is this? I mean, what do you remember the word for something that's not part of your main chain? It's something that's attached to it. It's called a substituent group. How do you name a 1-carbon substituent? Methyl. It's called a methyl group. Okay. And which number carbon is it attached to? Okay. So this is methyl. It's on the 3rd carbon. The last part is this cis or trans? Cis. The ends of the carbon chain are both on the bottom. That's cis. If they're both on the top, that's also cis. Trans is if it's top, bottom, or top, bottom. So this is cis. Okay. Depending on which textbook you use, you know, if you go on to college and you take organic, sometimes they'll put cis and trans right at the beginning of the name. Sometimes they'll put it towards the end. It really doesn't matter. It's probably just easiest to put it at the beginning. When I learned organic, I learned it, you put it towards the end, but it doesn't matter. Okay. Questions on that one? So again, am I going to have to worry about cis and trans in number 1? No, because unless you see that X shape, you don't have to worry about it. So you're going to name this one. The ones on the bottom, I'm going to have you draw. Okay. And remember, for those of you that were here last class, I gave you some options on how you draw things. You can either draw, you know, CH2, CH2, CH3, or you can draw every single individual bond. It's up to you. One last piece of advice before you get started. When you're given a name and you're supposed to draw it, my suggestion is kind of work your way backwards. Start with the longest chain, draw that first, and then start worrying about things attached to it. Okay? So give this a try, see how you do. All right, check your answers, ladies and gentlemen. I have drawn this. I have drawn 3 and 4 in 2 different ways, and I don't care how you go about it. This would be drawing every single individual bond out. If that's annoying to you and you feel like you've got a handle on, I know how many hydrogens are going to be attached to each carbon, you're welcome to do something like this. This is what I typically will do. Like, I'll show the bonds within the carbon chain, but I don't show the bonds for all the individual hydrogens. But you can. It's totally up to you. And when you are doing the drawing, you get to decide, am I numbering from left to right or right to left? It's up to you. Okay. So here's 5 and 6. Yours may not look exactly like mine, but as long as it fulfills all the requirements within the name, we're in good shape. Oh, the only reason I wrote it like this was just so you could a little bit more easily see that this carbon is connected to that carbon. But I could have written it as CH3 as well. Okay, how do we feel about this, okay? I'm going to give you some more practice at the end of class today. Okay. Now, I told you guys last class that the thing that makes college organic chemistry so difficult is not the nomenclature, it's not the drawing, it's what they call the mechanisms. It's just multi-step reactions. We're going to do a few reactions. We are only going to do the simplest of the simple because I don't want to get into the really difficult ones. Okay? This first one you already know. All right? What makes something a combustion? What's the one defining thing? You're adding oxygen. Okay? Well, guys, if you combust any hydrocarbon, and I do mean any hydrocarbon, any compound that has carbon and hydrogen in it, you will get the same products every single time. You will get carbon dioxide gas and water vapor. Okay? If you decide to drop a lit match into your gas tank, which you won't, but let's just say you had like a crazy moment and you wondered, gee, I wonder what'll happen. Okay? Well, when your car blows up, this is really what you would get. Okay? If you combust gasoline, these are your products. Okay? And the only tricky thing about these combustion reactions is that sometimes they are difficult to balance, but that's it. Okay. Here's another one, something called substitution reactions. Very often take place with halogens. Okay, and I'm going to draw this out for you. It's a little easier to see if it's drawn out. Forgive me for not drawing in all of my lone pairs. Okay. But what you end up getting is a substitution. Two things swap places. This hydrogen and this chlorine switch places. This is what you get. Okay? So this is substitution reactions very often happen with your diatomic halogens. One of the atoms in that diatomic halogen will switch places with something on a hydrocarbon. Okay? All right, here's another kind of organic reaction that comes up a lot. It's called a dehydrogenation. And let me draw this up on the board. All right, and I'll just draw the carbons just to make life easier here. Okay, what would the name of this compound be? All single bonds. Propane, okay. All right, well, watch what happens in a dehydrogenation. Dehydrogenation means taking hydrogen away. Look at what happens to something like propane. Okay. What's this called? Propene. Do you see that all I really did was remove two hydrogens? And if I remove two hydrogens, that causes a double bond to be formed. Okay. Why two? Because hydrogen is a diatomic element. Okay. If you take hydrogens away, you take something from being saturated to unsaturated. Okay. If you add hydrogen, you go from something being unsaturated to saturated. All it means is that pair of hydrogens is added across a double bond. Okay, so those are just opposite processes. Dehydrogenation versus hydrogenation. And it's not just hydrogen that you can add across a double bond like that. You can add anything diatomic. Okay? For example, give me one of the halogens that's diatomic. Chlorine. You could add Cl2 and it would get rid of the double bond. And instead of having an extra H and another H there, it would be CH2Cl, CHCl. But it would still get rid of that double bond. And that's what this is. It's called a halogenation. Okay. All they've done instead of adding 2 hydrogens across that double bond, they've added 2 bromines. Okay? And I love how halogens are named. Bromo. Okay? Fluoro, chloro. If it's iodine that got added across, it would be 1,2-diiodo pentane. But these are all processes that turn something unsaturated into something that is saturated. Something that has a double or triple bond to something that is all single bonds. Right? Okay. This is a molecule that when you go and take organic in college, you're going to see it a lot. Benzene is a very common organic molecule. And I have a little issue with this particular drawing out of your textbook because it's not quite correct. Benzene is a 6-carbon ring, but I'm going to add something to make it truly correct. Here's what's missing from this drawing. Right? Benzene is a 6-carbon ring, but it has double bonds on every other side, which is why the bond angle is 120 degrees. Do you remember what shape that is? Trigonal planar? Yeah. Okay. So I don't quite like that they didn't draw those double bonds in there. Now, because benzene is used so commonly in organic chem, and drawing all of this out is really annoying, they have some shorthand ways to draw it out. Sometimes you'll see benzene just drawn like this. What concept are they trying to illustrate here? Resonance. Benzene exhibits resonance. And because this, I guess, is just too much of a hassle, then they went down to this. Ladies and gentlemen, I am perfectly fine with you drawing benzene just this. Okay? That is the international symbol for benzene. You don't have to draw in all the hydrogens or anything. Okay? That symbol means benzene. Okay. The last thing in this chapter is a concept called functional groups. Okay? There are 6 of them that we're going to learn. There's more than that, but we're only going to learn 6. And just to help us get our bearings, are we all aware that there is no element R? Say yes. Yes. Okay, good. What R represents in this chart is your hydrocarbon chain. Okay, your longest chain. Functional groups are they're similar to substituents. They are things attached to your main chain, but they're not called substituents because these things that are attached change the molecule so much that they get their own category. They're called functional groups. Okay? So for example, this first one is showing that to your main chain, whatever that is, an alkane, an alkene, an alkyne, whatever it is, if you have an OH group attached somewhere, it doesn't have to be on the end, that has turned your molecule into an alcohol. So, for example, let's say I have something like this. Okay? Same rules apply. What's the prefix for 3 carbons? Prop. Okay, it's all single bonds in the chain, so propane, propene, propyne, what?
Propane.
Okay, so I'm going to put AN in the ending. Propanol. Okay? And to be even more accurate here, the name should be 1-propanol. Now, what do you think that 1 is telling me? Where that OH is. Because, guys, in alcohol, that OH can be attached anywhere. It doesn't have to be on the end. So what if I move the OH to the middle carbon? Then it's 2-propanol. Think about some compounds that you may know. I mean, rubbing alcohol is isopropanol. An alcohol that we use a lot in the lab, methanol. The alcohol that's in any kind of alcoholic drink is ethanol. All right? Ethanol is also used as an additive in a lot of gasolines. Okay? So now you know where those names are coming from. All right, let's look at this one. Let me explain what this is trying to say here. All right, let me draw it up here. This is saying that one of your carbons in the middle of your chain. So let's say something like this. Okay, it's not at the end, because if it's at the end, that's something else. A ketone has a C double bonded to O somewhere in the middle of your chain. Okay, what's the prefix for 4 carbons? Bute. Okay. All single bonds, right? So butane. And then look at the ending. Butanone. Okay. Think about some compounds that you know that end like this. What's the active ingredient in nail polish remover?
Acetone.
Acetone. Okay, now acetone is what we call a common name. It's not using our meth, F, pro, bute prefixes, but acetone is a ketone. Okay, now tell me this, guys. In this particular one, do I need a number here to indicate where that C double bond to O is? Do I need?
No.
Why not?
It has to be in the middle.
It has to be in the middle. So what if I move it over there? It would still be on the second carbon, okay? But, hold on, what if I did this? What if I added another carbon? Now I do. This would be pent, and what would the number be? 2. The only other option would be 3-pentanone. Okay, but again, it can't be on the ends, because if it's on the ends, then it's not a ketone. So what if it is on the end? What does that make? That makes what's called an aldehyde. So let me adjust my drawing here. Put it down here. Okay. So if your C double bonded to O is at the end, it's not a ketone, it's an aldehyde. Okay. Prefix for 5 is pent, yes? Okay. Pent what? It's all single bonds in the chain. Pentan, and then look at the ending. This would be we call it pentanal. Do I need to indicate a number of where this is located? No, because it has to be on the end. Are you ready though? What if I do this? Let me fix this drawing a little bit. What if I did that? How does the name change? Is it still an aldehyde? Yes. So what changes here? Okay. Do I need to input a number where the double bond is? Yes, I do. And what is that number? Okay. Yes, sir. The functional group. You have to, how do you know if the number refers to the multiple bond or the functional group? Well, you have to ask yourself, first of all, is this a functional group that requires a number in the first place? Aldehydes don't, because they're always at the end. Always. Ketones do require a number. Alcohols require a number. So I am telling you guys, I am not going to give you, I would not give you an alcohol or a ketone that also has a double or triple bond in it, because in all full disclosure, I don't know how you handle that kind of naming. Like, how do you indicate not only where the functional group is, but also where the double and triple bond is? I don't know. So I will only give you a double or triple bond on a functional group where it's a functional group that doesn't require a number. Okay? All right. 3 more. All right, how about this situation? Let me change my drawing a little bit. Okay. So this is still saying something on the end, but it's not just a C double bonded to O. It's C double bonded to O, and instead of just having a hydrogen in that position, now it's an OH group. It's not an aldehyde anymore. It's called a carboxylic acid. Okay, so, oh, I forgot to draw that bond in there. Okay, so pent, tell me how this one would be named. Pent, what's next? Okay, AN, and then what? Look at the chart. Pentanoic acid. Is that one of our strong acids? No. All organic acids are weak. All of them. I mean, think about it. Our 6 strong acids, HCl, HI, perchloric acid, none of those are organic acids. All organic acids are weak. Okay. How would the name change if I do, oh wait, that's not, sorry, that was wrong, there. How would the name change if I do that? Okay, an E instead of an A. Yep. Okay, carboxylic acids don't require a number to tell me where that functional group is because they're always at the end. Okay, now these last 2 are much, much simpler. Okay, there's really, I'm only going to give you ones that are not that complicated. Ethers, let me explain what's going on here. Instead of having something attached to your main chain, you've got something interrupting the main chain. Like that. Here's how we name ethers. Tell me, guys, how do you name a 3-carbon substituent? Propyl. How do you name a 2-carbon substituent? Okay. What comes first in the alphabet, E or P? Okay. All one word, ethyl propyl, space, ether. Ethyl propyl ether. Okay, you'll see, if those of you that are history buffs, ether was used as one of the first methods of anesthesia. Okay, if you've ever seen like documentaries on old, like the origins of surgical techniques and everything, you'll see pictures of people who they usually would have like a cloth or some kind of a cone over their mouth and nose, and they would pour a liquid ether over that cone or that cloth. Ethers are very, very volatile, so then they would breathe in these fumes and it would cause people to lose consciousness, and then they could operate on the person. Ether has some other very negative effects, so they stop using it, okay? But that's a place where you would, in everyday life, you might hear about ethers. I'm not sure what the formula is for that particular ether, okay? How would the name change here if I do this? How would that name change? Diethyl ether. Yeah. Diethyl ether. Okay, so ethers treat the either side of the oxygen, kind of like substituents. Very last one. Okay, amines. Nice and simple. Something like that. Meth-eth-prop. Look at how it's named. All one word. Propylamine. Okay? If this looks familiar to you, any biology people, like amino acids, okay? Amino acids are called amino acids because they have an amine group in them, okay? Or, here's another word that ends with amine, methamphetamine, okay? Like the drug, okay? Ooh, drugs, okay? Okay, so 6 functional groups. So guys, what happens, and I'm going to give this to you in just a moment, what happens if I give you a drawing and I ask you to name it, and this drawing has a functional group, a multiple bond, and various substituents? How do you handle that? How do you know? The real ultimate question is, how do you know how to number your carbon chain? Like, what's the most important? Well, I'll tell you. Number 1 in importance to be on a low number carbon is a functional group. If you see a functional group in your drawing, you can right away decide how to number your carbons, no matter what else is there. Because that is number 1 in importance, to be on the lowest number carbon you can make it. If you don't have a functional group, but you see a multiple bond, then that is the most important thing, to be at a low number carbon. Substituents are least in importance. Okay? The lower the number, the better. So, I have put together 3 drawings that have all 3 of these things in them. You're gonna love this. I think this is so fun, but my idea of fun is a little skewed. Are you ready? You're gonna love it. All right, let me pull up the first one. I've given you drawings. I want you to name it, and I've been nice, and I've just included the carbon backbone. I didn't include all the hydrogens. Here is your first one. Name it. All right, are you ready for the big reveal? Okay, here we go. Let's see if you got it. Oops, back. Hold on. Okay, let's talk it out. Are we all okay with the fact that it is a carboxylic acid? Okay. What is the most important thing to be on a low number carbon? A multiple bond, a substituent, or a functional group? A functional group. This must be carbon number 1. No matter what else is going on in the compound, if you see a functional group, your functional group needs to be on the lowest number carbon possible. That means this one has to be number 1. So 1, 2, 3, 4. That 4 is telling me where the double bond is. Okay. How come I wrote in the name ethyl before methyl? Alphabetical. It has nothing to do with the numbers. It has to do with writing them out in alphabetical order. Okay, are you ready for the next one?
Yeah.
Yes, this is fun. I know, you're excited. I'm excited too. Oh, there's your next one. Oh, it's so awesome. You knew I was going to throw a cis and trans in there. Okay, here we go. Noni now. Yeah, be careful saying noni nol, like, because some words that end in al in English we do pronounce with an all sound, but in organic, if you say noni nol, that makes me think it's an alcohol, which it's not. Okay, so I say noni now. And what type of functional group is that? Or what type of compound is this? It's an aldehyde. All right, are you ready for the last one? This one's my favorite. It's actually really cool.
Maybe like 2 X's.
Wow! Oh. What? What is happening? Ooh, it's a cyclic molecule. Okay, last one.
Oh, I think you have to ask.
Wait, why are they doing that?
All right, let's talk it out. Having an OH attached to a carbon chain makes it what? An alcohol. Okay. Now, alcohols can be joined anywhere, but when we're dealing with a cyclic molecule, when you're trying to decide how do you want to number this guy, aren't functional groups the most important thing to be at a low number? So I'm going to make this corner carbon right here, I'm going to make that number 1. So I don't have to include where the OH group is located, because no matter where I put it, that's going to be number 1. Okay, now why, guys, is it correct to number counterclockwise as opposed to clockwise? Because the triple bond is next in importance. So that's what that 2 is referring to, is where is that triple bond? And then my numbering system is set up. C comes before M, chloro, methyl. Okay. And that is the last lesson of the whole year. No, I'm not crying, actually. That's it, ladies and gentlemen.